Alrighty. Okay, so hi everyone. This session is going to be on ROP, return-oriented programming. This is one of the coolest parts of binary exploitation due to its prevalence in today's exploit environment. On the previous sessions, you looked into shellcodes. So when we do shellcodes, we have to do something that's called, I'm going to write it here, code injection. Can you tell me what is the downside of using code injection, of using shellcodes?
Is that you need an executable stack?
Yeah, so you basically need simultaneously, you need write plus execute permissions. And that's a downside. Usually that's going to be the stack or the data section or the heap. Now these are usually rendered as read-write, so no execute. That's also the bit, it's called no execute, or it's called execute disable. So this is called execute disable. This is how it's called on ARM. And no execute, this is how it's called on x86, no execute. So once again, this is the terminology on x86 AMD, whereas this one is the one used on ARM. Because you have those read-write, you aren't able to use code injection. You have to do some sort of mprotect magic to be able to remap those memory areas as write execute. That's going to take some time. So code injection isn't actually useful at the starters. What we need is something that we call code reuse. By code reuse, we mean that certain parts, certain chunks of executable of already executable data sections of executable sections, such as the code section, are reused. And how do we do that? The most simple one is to actually just call functions from there. The other one is to reuse even smaller parts of the functions. And to see how that goes, let's look into these examples. So what we have here, we have a C program we're going to look into, and we have two make files. One is for, if we look here, this one is simply for compiling this for 32 bits, whereas the other one, makefile 64, is for compiling it for 64 bits, right? So we have these two executables. If we do a file on them, we're going to see that this executable is for 32 bits, 32 bit i386, and the other one is a 64-bit one, right? Also, I think you know of I don't recall. I have a memory lapse. How do you call the tool that gives you information about the security? How do you call it? Secinfo?
Checksec.
Yeah, sorry. So if we do a checksec, this is 32 bits, and if we do checksec, this is for 64 bits. Okay. So this is what we start with. Let's look in the program. So what does the program do? It has this main function, and as part of the reader function, we have a buffer overflow. This is very easy. There's a 64 bytes buffer, and we read 128 bytes in it. So this is fairly simple. We just read it and we overflow it. We are thus able to overwrite the return address. And here we have four functions named after Blizzard Entertainment games, which do different things, and we're going to see how we can exploit them. For starters, what we aim to do is use this buffer overflow to do the most basic code reuse action possible. The most basic code reuse action possible is calling a function. So we're going to use this buffer overflow once again for the simplest code reuse action, calling the Warcraft function. So let's do that. Let's use this program. Let's use this buffer overflow for this very simple action, calling the function. For this to happen, we need to know some things. One of them is what is the offset from the buffer to the return address, and then we also need to know what is the address of the Warcraft function in the executable. So once again, we need two things. The first thing is the offset from the buffer to the return address. That's the first one. And the second one, we need to know the address of Warcraft. Oh, sorry. These are the two items we need. Let's wait a bit, 1 minute, to make sure that everything is clear until this point. I may have been moved a bit fast. I'm assuming you know what's going on with buffer overflows. I assume you know a bit about the return address being overwritten. We need the offset, we need to find the address. But if anything is even the tiniest level of unclearness, let me know. Let's just wait half a minute and make sure that everything is clear for everyone. If any questions, please interrupt me at any given time. If no reaction, I'm going to assume everything is clear until this point. So once again, please, any small detail that's unclear, let me know. This is a demo. I'm going to also push it to the repo so you can look at it afterwards. If anything is unclear, once again, please stop me and I'll make things clear. It should be as clear as possible for you guys to reuse it and then make the best of it for the challenges in this session. Okay, let's work on this. So for starters, let's just move on with the 32-bit version, and for this we're going to use PWN tools script. So yeah, let me just. So what does this look like? I created a small skeleton. Let's just look through it and make sure everything is clear. Is this text size big enough? Do you want me to make it bigger? How is it for you?
You could make it a little bit bigger.
Okay. Is this better?
Yeah, it's perfect.
Alrighty. So what we have here, this is a part of what we call the context in PWN tools. I'm setting it to info. If you want to set more information, we can set it to debug. This is kind of the default level. I'm usually adding it as part of a PWN script to quickly change it to debug if I want to find out any other info. What I'm then using, I'm not going to use, I'm assuming in the past sessions use something like nm. You used nm on a given executable, and you are able to extract the addresses from here, right? So the StarCraft address, Warcraft, Overwatch, there should be Diablo, I think, above. Yeah, so I'm assuming that's the way you did it until now. I'm assuming if that is the case, you may have used other tools. There's also redelf that you could use, some others. Fortunately, PWN tools has some very nice way of doing it. If you do this, if you use elf on the executable image, and then you say e.symbols of the symbol name, provided the executable is not stripped, you are able to extract the address. So this is the way. Let me also add the StarCraft address. This is the way we're going to extract all the addresses from the executable. And let's just close it here, 0, and let's just print the addresses, right? So let's say print Diablo is at this address, and for this let's say okay, this should be it. Format, oh sorry, Diablo address. Okay, and let's do it for the others. So we have Warcraft. Now let's do it like this.
That B in that E dot symbols in brackets is due to Python 3, right? Or
I'm not sure what can you repeat that?
that B in E dot symbols in the brackets.
Yeah, the B. Yeah, the B. Yeah, it's because Python 3. So you have to prefix this with the B for Python 3. I'm usually using Python 3 due to its superior set of features. It's a bit of a pain when you go into this B part, turning strings into byte strings. But once you get adjusted to it, it should work. So if you were to use Python 2, you wouldn't be using the B in front of it.
Okay, thank you.
Yeah. So this is also, so this is for it was for Overwatch. Just a sec. Okay, and for StarCraft. Okay. So let's see how this goes. I'm going to run it. Okay. So this is how we extract all the addresses from the from here. What I usually do is if I know this is on 64 or on the 32-bit, here is on 32-bit, I usually do it like this just to make it sure it's using the whole set of hex digits. So these are the addresses. We are able to very easily extract them from here. So if we recall what I mentioned at the very beginning, we require two items. One of them was the offset, and the other one is the where is it? I may have written it somewhere else. I'm missing it. So one of them is the so once again we need the offset. And then we need the address, right? So we are able to find the address. This is done using this PWN magic with E dot symbols. And the other one for the offset, I'm just going to use an object dump and check the executable. And I'm going to look in the reader function. And if I look in the reader function, I'm going to see that, all right, the buffer is EBP minus 40. This is going to be used for fgets, right? So this is the buffer, it's printf. We can also see that ESP is decremented by 40 hex. So what we have is the buffer address is at EBP minus 0x40, and we also know that the return address is at what? Where is the return address? This is a question for you.
EBP plus 8.
Yeah, so it's EBP plus
Hex 8.
0x8, right?
Yeah.
Okay. Why is it at EBP plus 0x8? Anyone? Why is it at EBP plus 0x8?
Because it's just above the current stack frame, the return address.
Okay, shouldn't it be EBP plus 0x4? What do you think?
It's EBP plus 0x4 on 32 bits and plus 0x8 on 64
Okay,
bits.
so it was actually RBP plus 0x8 on 64 bit, but since we are on 32 bits, it's EBP plus 0x4, right? That's where the return address is located. This is what you learned from the previous sessions. Let's once again wait half a minute, make sure we get this. Once again, if anything is unclear, interrupt me, say this is not clear to me, please repeat it, there's no problem. So this is kind of building up until we get to some actual attacks. So please make sure that each step is clear for you. If any step along the way is kind of messy, unclear, in the fog, complain, let's go through it. Right, I'll assume that everything is okay. So then, because the buffer address is EBP minus 40 and because the return address is EBP plus 04, then that means that the offset is 0x44, right? Difference, so let's call it like this, just a sec. So buffer is at 0x, EBP minus 0x40, and the return address is at EBP plus 0x4, right? So then we create the payload. How do you do the payload? The payload is going to be the offset. We're going to multiply the offset by A, and then we're going to you do P32, it's actually going to say, what was it? I think it was pack. It should be little endian, and it's going to be a Warcraft. Yeah, we wanted to see the Warcraft address. Now I don't know, let me do something here, let me see if indeed, I don't know for sure what the just a sec, I don't know, I don't recall what this pack was, so I want to use the proper way. No, it should be system sh present, just a sec. Pack. Oh, we have no pack here. Let me see, I'm not sure.
Maybe P64?
No, that I don't want to use that one. I want to use something that's generic. So it should be
Okay.
just pack. Okay, so pack does it. So the thing is, it has this kind of pack, very nice macro, but this pack has to know the context. If the context is the binary, and this guy is going to tell it whether it's 32-bit or 64-bit. If you see here, it says the arch is 32-bit, so that gives you the context. And because of the context, it is able to infer whether the packing should be on 4 bytes or on 8 bytes. And currently it's going to be on 4 bytes. That being said, let's make sure this is indeed okay, and we're going to call the function above print byte array. So print byte array we're going to say the payload is payload, and let's see how this goes. All right, so this is the payload. These are all the A's, and then we have 08, 04, 84, B6, 08, 04, 84, B6. This is Warcraft, right? So it's okay, everything is fine. We were able to create the payload. Now, because we have the payload, let's feed it to the program, and if we feed it correctly, it should bring out the message from Warcraft, which is chieftain. Let's see if that works. Python, whoa, exploit.py, chieftain. Awesome. So we were able to create this exploit and call the Warcraft function. This is the simplest code reuse attack possible. You get a buffer overflow, and you are able to override the return address with the address of another function inside the code. In our case, it's the address of the Warcraft function. I'm going to do something different now, and then we're going to wait a bit to see if it's clear. look at what I'm going to do, and then make sure it's okay with you guys. So vuln. Okay, so let's look into the Warcraft function. No, let's look into the Starcraft function. And in the Starcraft function, I'm going to get this address 08 whatever. I'm going to do it here. I'm going to say, let's say Starcraft inner address, and I'm going to say it's equal to this 0x0 here. And then when I create the payload, I'm going to create it using this Starcraft inner address. Okay, let's see what's happening. It prints Caprulu. Let's see why that is the case. If we look here, no, not this one, just a sec. We were able to print Caprulu. So what did we do here? Why did I use that internal function address instead of using the Starcraft address?
You wanted to avoid the condition and just jump to the call?
Yeah, so what I basically did, I simply jumped to the location where that print call is made. If we look in the Starcraft function, this is where the argument is pushed on the stack, and then the puts function is called. And I was able to avoid this comparison by simply jumping at this address. What I want to show by this is that when we do any sort of code reuse attack, we don't necessarily use a function address. We can use any code address there is. That can also be some of the address of another instruction inside the function. Even more than that, and this is something very interesting that can be done in x86, I could jump, for example, to this address 8048520, and I would jump to this address. Of course, if these bytes were going to be interpreted by let's say the instruction pipeline as an instruction, you would be able to look at them as such. So this is something very interesting that's not possible on ARM, because on ARM any instruction has to be aligned. In x86 the instructions can be at any location, and you could interpret any instruction as any sort of address as the beginning of a new instruction. So not only would I be able to jump at these addresses, but I can basically jump at any address. But of course these addresses have to contain valid instructions. So kind of apart from using the address of a function, I could use the address inside the function as part of a code reuse attack. Now let's wait 1 minute to digest all this info, and let's see if you have any sort of questions.
So this means there will be some instructions that are not used in the original source code.
Can you repeat that? So there will be some instructions that
are not used in the code.
Well, it depends. I mean, the code that I'm going to reuse is any code. That code may be used by the actual program flow, or it may not be used by the program flow. In this case, yeah, these functions that you see here are what we call hidden functions. They aren't actually called, but I could call them with no problem, right? So it really doesn't matter for my purpose if these functions are called or not. They may be called, they may not be called, it doesn't really matter. For me, for the attacker, it only matters that these functions or these chunks of code are part of an executable memory section, and I'm able to jump to them and execute them. If they are called by the program or not, it doesn't concern me. I'm only after their certain effect they have. Of course, in this particular case, it's really stupid to kind of consider, yeah, I'm going to call StarCraft because the program doesn't call StarCraft. This is only a teaching example, right? In an actual program, you wouldn't have this. In an actual program, in the real world, you expect that all these functions to be used by the program, but what you want to do is maybe call those functions in a different way, such that you kind of give a different behavior to the program, or something different. You are able to call functions from outside the program from libraries that are loaded by the program that give you some sort of leverage as the attacker. So don't get this example as this is the way attacks usually happen. It's not that. The mindset should be, I have this set of instructions spread throughout the program. I want to reuse them for my particular purpose. That purpose may be leaking some data, calling, getting an mprotect call to be able to inject shellcode, calling a system of binsh to open up a shell, opening up a socket. It really depends on your interest as the attacker. All right, moving on then. Let's now see how can we call different functions. So what we have until now, we have Warcraft. Let's assume we also want to call Overwatch, right? Now we called, let's not do Warcraft actually, let's just call Overwatch. Let's see what we have to do to call Overwatch. So we look into the vuln.c and the exploit script. And here we see that if we want to call Overwatch, we have to pass it an argument, right? We have to pass the deadbeef. Of course, we have this kind of very nice idea of simply jumping here for the cheers love message, but let's do it properly. Let's aim to jump at the Overwatch function and pass the proper argument such that this check will hold. So in order to do that, we want to go into the Overwatch address, but if we just use it here, of course the argument is not going to be passed. So if I do now a python exploit.py, this will not work. It won't show me anything. So what do I have to do is actually I have to do something such that Overwatch is going to get this address. So what I'm doing then is I'm going to do something like this. I'm going to add 4 bytes, 4 Bs, and then I'm going to pack the argument expected by Overwatch, and the argument, if we recall, is deadbeef. So let's do this. And now I have a payload that is going to call Overwatch. This is the expected Overwatch return address, and this is going to be the argument, right? Let's see how this goes. Okay, so we get the cheers love message. Let's wait a bit. This is again something you should have been part of the other sections, the way you kind of pass an argument to the program. Let's wait a bit on this again and see if it's clear for everyone. Sorry if I'm a bit too slow making some breaks, but I really want to make sure that everyone is on the level with this. If anything please interrupt me. Pretty unusually for me, I'm going to want to fall more on the boring side than I'm going to fast side.
Can you explain again why do we need that 4B padding?
Just as a clue for me, I haven't been part of other sections. Didn't you guys use this 4B until now anytime? It's okay if you didn't. I just want to know how much in depth should I go about explaining it.
So my guess is that you basically put on the stack.
No. Once again, sorry. I can explain it. I asked a question. In the previous sessions, did you encounter this 4B notation for passing arguments to functions, or this is the first time you're encountering it as part of the Security Summer School binary sessions?
I don't think I speak for everyone, but I don't remember seeing this.
Okay.
Me neither.
Okay, so it wasn't part of the summer school. Okay, got it. Let's then do a show on this. So this is what I'm going to show here is going to be the stack, right? So this is going to be the stack. These are going to be the what I call low addresses, and here we have high. No, sorry, these are high address. Sorry, low address and high address. Just a sec. Okay, so the stack is going to grow down. So here, somewhere here is the buffer. This is where the buffer goes. At a certain point, this is going to be where the old EBP is stored, and this is the return address, right? So the buffer goes from here, and then we have the old EBP, and then we have the return address. What we are going to do here is we're going to replace this return address with the Overwatch address, right? This is what we do so far. That means that when the Overwatch address is going to get called, this is where the stack is going to be located. So once we're going to call Overwatch, this is the top of the stack. When you call a function, when you call a function in a good way, how do you call it? What is the assembly way of calling a function?
Push ABP mov
No, that's
ES.
not the way of calling it. That's a way of what it's doing after it's being called. What is the assembly way of calling a function? It's actually what we call in Romanian murangura, what I'm asking.
Well, for 32 bits, you have to push the arguments on the stack.
And then
call the
function.
And then issue call, right? So you're going to issue call the actual address. So what's actually happening as part of call? As part of call, what's happening is you do push next instruction address, or if you want, save next instruction address. This is actually store the return address. This is what's happening. And let's say call F, and then you're going to, so this is one of them, and then you're going to jump to F. Yeah, this is going, so this is save the next instruction address, which is similar to, let's say, saying push EIP, push the next instruction, and jump, and then jump to it. So when Overwatch is going to get called, what it expects on the top of the stack is this. It expects its return address. So here is, let's say, expected Overwatch return address. And as you guys said, somewhere before that you would have something like push third argument, push first argument, second argument, sorry, push first argument. let me put them a bit because these are pieces of code, and okay, so that's the code. And here is expected first argument, and then expected second argument, and so on. So then this is, I'm going to get all of this out of the way, right? Just to make sure now we have what the attack should look like. This is the stack, right? High address, low address. This is what the stack should look like based on this. When Overwatch is going to get called, this is where the stack is going to be. This is going to be top of the stack, and because it assumes it was called validly using call, it expects on top of the stack it will have the old it will have the return address every time at the beginning of each function. Because it assumes it was called using call, it expects on the top of the stack the function address. Then on top of then below that you'll have the first argument, then below that you'll have the second argument. And in this way, what we are doing here, we are overwriting the return address with the Overwatch address, and this is kind of the expected return address, and this is the argument. So then let's do it a bit like this to let you guys know what's happening, and then we can get back to analyzing this a bit more. When I'm doing this, it will say cheers love, and if I do a DMSG, you're going to see that the segmentation fault happens at 42, 42, 42, 42. What is 42? If we look into ASCII, we see that 42 is B, right? So it's 4 B's. So what it did is actually it executed the Overwatch address, the Overwatch function. It did its tricks, and then the Overwatch function tried to return to this return address. I just added 4 B's, and it tried to jump the 4 B's, 0x 42, 42, 42, 42, and because it wasn't a valid address, it cracked. So that's what happened. This is something that you need a bit more time to get accustomed to. It's not something that you look once and say, everything is clear. You do it once, you do it twice, you do it thrice, and maybe I think the 5th, 6th times it kind of makes sense. You can get it, okay, maybe now you have some idea. It's not completely clear. It's okay if it's not completely clear. Once you exercise it a bit more, you're going to kind of reshape your mind towards understanding it. For now, let's wait a bit. Let's wait 1 minute to make it sure you grasp it, and then see if there are any kind of fundamental questions on this. If it's not fully clear at this point, don't worry. It will become clear as you exercise it more, and then it's going to make sense completely. But let's just wait 1 minute more to make sure you grasp it. Okay, any questions here?
So basically you can chain multiple functions with
Yes.
these.
So now what we can do is we're going to replace this 4B with pack of Warcraft address. And now what's going to happen is that we're going to call Overwatch, and then with this argument, and then Overwatch is going to return to the pack Warcraft address. And let's see how that goes. And now we have Cheerslov and Chieftain. Can you tell me, based on this, what is now the return address? I mean, so we called Overwatch, and when we called Overwatch, the stack was here. So let's look at the stack. So we have Overwatch, now we have Warcraft address, and we have, let's say, expected first argument, right? So this is where the let's say top of stack at the beginning of Overwatch. This was it. Now when it ended, it got the argument, it consumed the argument, and then it simply popped this address and it returned it went to the Warcraft address. The moment that when it went there, this is the top of the stack at the beginning of Warcraft. Righty? So this is where we are located at the beginning of Warcraft. It should actually be one only G and here. So can you tell me, this is the top of the stack, what is the return address of the Warcraft function?
It should be deadbeef, right?
It should be deadbeef. Let's see. Sec fault at deadbeef. Right. So now what happened is that this first argument is kind of the return address of Warcraft address. So what you did so far, we are able to call Overwatch and then call Warcraft address, but that's it. We can't call anything more, because then Warcraft is going to be stuck on this. If we change this to something else, it wouldn't be able to call Overwatch. I mean, we can say here, for example, pack of Diablo or something like this, but then it wouldn't call Overwatch properly. So we are kind of in a conundrum. If we want to chain together multiple functions, we have this issue here. This argument needs to kind of simultaneously be the argument of Overwatch and then the return address for Warcraft. So what do we do? Is there any way of toying around that? And yes, it is. There is a way towards that. How do we do that? Well, let's assume we want to get rid of this argument. We need to remove it from the stack. So how do we do this? Let's just say here pack of Warcraft address. Let's add it afterwards. Warcraft address. So we need some way in which we are able to call Warcraft address but somehow get rid of this. So what can we add here that allows us to get rid of this? And I'm going to say here, just a sec, I'm going to go into a pop red gadget. We're going to discuss it in a short gadget. Let's just see what this should be. So what I'm saying is this: instead of using the Warcraft address here, I'm going to say this pop red gadget address. What this is going to be? This is going to be the address of a small chunk in a program binary instruction that's going to say something like pop, let's say EDI, and then it's going to be followed by ret instruction. This is what I call a pop red gadget. What will this do? The moment it jumps to pop EDI, it's going to pop something from the stack. which is this. And because then I'm going to say Warcraft address, it will then pop this argument, which I no longer need. I want it to be removed. And then when it's going to get to do ret is basically a call. Ret is equivalent, so if we go here, ret is equivalent to pop what is on the top of the stack. This is what ret does. No, pop, call, sorry, call. Or yeah, pop as well, whatever. Let's say call ESP. It calls what's on top of the stack and simultaneously popping it. Yeah, so it calls what's on top of the stack. Okay, this sounds a bit weird maybe. Let's just look at the way how we find this pop rob gadget address. Let's see this if this works, and once this is going to work, we're then going to take a look into it. This is why it's going to be called return oriented programming, because it's using all those return based gadgets. Let's add it here, pop ret gadget address. Whoa. And let's see how we find it. There's a tool that's called drop gadget. We're going to serve it this argument vol, and let's just look at this is a tool that finds these gadgets. Let's find the pop ret gadget. Pop EBX ret. This is one of I don't care what register it's using, I just want it popped. So then I'm going to use it here. This is a pop ret gadget, and let's see how this goes. Cheerslav and Chieftain. It worked. Take 2 minutes to look at it, and then we can discuss it more.
And basically that gadget is just code somewhere in the memory of the program. It's not something we added,
no,
right?
It's code reuse. Yeah. Okay. So what I said is that when you reuse code, you aren't necessarily reusing entire functions. You can basically reuse just chunks. And one of these chunks, some of these chunks are called gadgets. They are specifically called ret gadgets. They can be jump gadgets, some call gadgets. These are ret gadgets. It's a chunk. If I do an object dump in the executable, ob jump, where was it? Just a sec. And let's look for, yeah, this is it. This is my address, pop EBX ret. So this is where it's located. Rob gadget simply looks in the binary, looking for this Rob gadgets. It's going to find them, and yeah, then it works. This is code reuse. Finding small pieces of existing code and then reusing them.
So basically within each function call we have to use this pop ret gadget.
So let's do it let's do this a bit differently. Let's aim to call I think it was what was it? Was the Diablo function. It has 2 arguments, right? Let's try to call Diablo then Warcraft. If we were to do that, let's do another payload. It will be like this. It will be Diablo address. Then we're going to have a pop ret gadget because it has 2 arguments. The first argument is so it has 0, 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the other argument is 0xAA, BB, CC, DD. and I need a pop red gadget. So I'm going to look for that pop red gadget address. Let's look through it. Pop red. Do we have one? Pop red? Yeah.
Can't you call also that pop red 2 times?
Yeah, that's also an option, but it makes it easy if we had, yeah, of course, we can call it, we also have a pop red. Yeah, we could call it twice, of course. So we have this pop red. I'm going to copy it. It's going to be here. And now let's see if it works. Worldstone and Chieftain. So we were able to do something similar, except now we are able to call Diablo, and then we were able to call Warcraft. If I want to make this even more interesting, I could call then this pop Overwatch address plus pack of no, only one pop gadget address, then plus a pack of 0x dead beef, and then plus pack of Warcraft address. Yeah, I think I know it's a mouthful. And now I'm pop gadget. What am I missing? Pop red, sorry. Worldstone, Cheers Love, Chieftain. Voila. We have them all. Summarizing this a bit and then getting those 2 minutes of well-deserved break and thinking time. This is very close to how current attacks happen in the binary. I mean, you need some sort of ROPs, you need some sort of code reuse. This has been on for, I think it's going to be close to 15 years, 12 years. It's very often used because you don't need anything special. You're simply able to reuse existing code. So this is very important. It's a bit difficult to understand because of all those kind of toying around with the stack in order to be able to execute code. So I know it's kind of a bit of a headache. It takes a bit of time to work through it. That's why this is the first session. And then we have another one, we call it Advanced ROP. We're going to once again go through things and tie things together. But for starters, this is a good approach. It's not going to be, once again, totally clear from the starters. You need some sort of adjusting time to it. As you work more on it, it becomes more clear. Then you need to work a bit more. But it's very interesting, it's very modern, it's the way things happen, and in time it will become fully clear as you work it. Practice makes perfect. Now let's wait 2 minutes to see if it's okay for everyone, and then we're going to do questions, and then I'm going to ask you to spend 15 minutes more to do something on the 64-bit side before moving on to team breakup groups and working on actual challenges.
Question?
Sorry, was that the question?
Oh, yeah, so in order to make things more clear, we use those pop instructions in order to make space on the stack for the arguments.
It's actually, you have the arguments on the stack as part of the payload. They are on the stack. You want to remove them from the stack in order to be able to call other functions, because if they are on the stack, they are going to make it more difficult to call out the functions. So we need those two arguments, let's say the ones here 0x1 2 3 4 and AA B B C C D D, we need them on the stack, but then when we call overwatch address we need them removed, and this one is the one that's clearing them. So they are part of the payload, they are put on the stack, and then once you execute this gadget you're going to remove them to move on with calling other functions. You can see them as a way of clearing up the stack for future function calls in this particular
And
case.
it is in reverse order.
What do you mean in reverse order?
I mean, the arguments are put first and then they are removed. But in the code, it's reversed. The op is first and then the arguments.
Yeah, that's because once again, once you go to the once Diablo gets called, as we see here, let's say this is the Diablo address, now it's called Overwatch. It expects on top of the stack, so kind of the stack goes from here and it goes down. So the stack goes down from here to here. It expects on the top of the stack to have the return address. So it's going to look for the arguments lower on the stack. It's going to use them, but then when it returns, it's going to use this value which is on top of the stack. So that's kind of where they are placed in different order, because that's how functions behave. Any sort of function expects on top of the stack its expected return address here, and then right below that it expects the first argument, and then they expect the second argument, and so on. That's because the way the stack is laid out.
Yeah, I get that. Thank you.
Okay. Once again, I don't kind of assume it's going to be all clear and all flowers and butterflies. I know this a bit difficult. You just have to know kind of, this is a kind of, I get the general idea, and then we can move on. Once you practice, it will become more clear. This is it. There's no kind of magical solution. You can't spring magic dust and turn from nothing to knowledge. There is no heaven, the doorway going to open. You need a bit of work, and once that is done, things will definitely become clear. Alrighty, any other questions? I'm going to commit this as it is with comments and with this kind of diagram in the repo, so you guys can look at it as it is. But before that, let's do something similar to the 64-bit function. So for this, let's look into vuln.c and let's look into exploit64.py. So this is very similar to what we have here, except that we have to look at the, so let's copy, let's just copy from the vuln.c exploit64 and exploit.py. Let's just copy these items and the offset and the payload construction. Okey-doke. So we have to know what, so now we know that the buffer is at RBP plus RBP plus 8. We now have to see where the buffer is located, because it's going to be different, and we'll see how that goes. Let's just wait sys exit of 0. Oh, just a sec. Let's also make sure that we print the payload. I I removed that. Oh no, it's here, sorry. Okay, so let's also print the payload. Because we are on 64 bits, we're going to say 16 here. Oh, okay, doke. And we also have StarCraft. Okay, doke. Let's find the buffer address. Von64. We go into the read function, reader, and then we see the buffer is RBP minus 40. So nothing out of the ordinary here. It's the same thing. It's at RBP minus 40, which means that the ACK address is now 0x48. This is the payload. Let's create the payload, and very similarly to what we did before, we're going to call the Warcraft address. Let's see how this goes. I did something wrong. I didn't send the payload. All right. Okay, so it called Chieftain, so this works okay. This is the same thing. I'm just sending the payload. I had to replace update the offset, and then I'm calling the Warcraft address, right? Now let us do something similar, and let's call Overwatch with the argument. So I'm going to say I'm going to pack Overwatch address, and now when doing the Overwatch address, I'm going to pass it as argument, right? So let's look in the argument that we have. We know it has dead beef, right? Just a sec. So we should say something like plus pack of this, right? So we're going to pass the Overwatch address, going to pass the dead beef argument. We need now kind of this 8b. We need 8 now. Why do we need 8?
Because an address has 8 bytes on
yeah,
64
because it has 8 bytes on 64-bit, right? So we're going to pass it here, and we're going to call it, and it doesn't work. Oh, we have to have a B, and it doesn't work. There's no cheers love message. Why? Why doesn't it work on 64 bits?
Because arguments are in registers.
Yeah, because arguments on 64 bits are passed on registers. They are not passed in on the stack. So actually we need this value to be part of the RDI register. Well, fuck, how do we do that? How do we make this value part of the RDI register? Well, actually we have to do it like this. So I'm going to give you guys the payload, and then we can see on it. We need to do some sort of pack pop RDI ret gadget address, and then we're going to add this stuff, and now we can call the Overwatch address. So let's at first look at it like this. Let's look at finding a pop RDI ret gadget address. Pop RDI ret gadget address. Let's find it, and then we're going to see if it works and then explain it. Rob gadget Von64. Let's look for pop RDI. Here it is. It's usually very easy to find. This is the pop RDI red gadget. We have that beef, we have Overwatch. Let's see it. Booyah, it works. So it did work. What did we do? Why does it work like this? Let's look at a bit of the stack, how it behaved. So we had the buffer here, then we had some info, and then we had the old RBP, let's say call it saved RBP, and then we have the return address, and then other things. What did we do? We replaced this return address with pop RDI ret. So this means that this went to a location where we had pop RDI, which was then followed by ret. Then what we put on the stack, we put 0x, we actually put dead beef, such that when pop RDI gets called, it's going to call from the stack this value and pop it in RDI. So pop RDI is basically similar to, so this pop RDI is something like move in RDI, what's now on top of the stack. So it's moving this value, popping it, removing it from the stack. And then before this, we're going to add the Overwatch address. And now this is going to be used by pop RDI, and this is going to be used by ret. And that's why it works. Let's take 1 minute to chew on this.
I have a question.
Please.
What happened if you literally found no pop RDI in the program?
Yeah, it won't work. As we say it when speaking Romanian, shit happens.
So let's say, sorry.
Yeah, so what you have to do then is actually, let's assume something in the register and you don't have a pop for that. You can look for other instructions. Maybe you have some sort of pop in another register, and then that register, as you look through the code, you see that there's some way of moving some information from that register finally in the RDI. So what you then have to do, this is the most interesting part, you have to chain gadgets together. So gadget chaining, getting them together, is definitely the way to go, is definitely the way to move when doing things. But this requires a lot of ingenuity. What we do here is something very simple. It may be a bit complicated until you get accustomed to it, but it's very basic. For those attacks that happen in the real world, they are looking extensively. It takes months for them to look for gadgets, chain them together, make sure a given register has a given value. This is where human ingenuity and creativity come into play. As we say, if it were simple, everyone was doing it, would be doing it.
So when you use the pop RDI instruction, does the top of the stack also, is the top of stack also removed?
Yeah, so pop is similar to move RDI, and something like, let's say, add plus add RSP8, so kind of increasing the stack and removing it. Yeah, So popping is similar to initialization and decrement and removing something from the stack. That's what pop does.
Okay.
All right. That being said, let's do just one gadget. Now we called Overwatch. Let's call Overwatch and let's call Diablo as well. Because we have to call Diablo, we recall that Diablo has 2 arguments. And for that we need something like pack. What ideally we need a pop RDI RSI red gadget. Because the RDI is for the first argument, RSI is for the second, is for the other argument. So we need this address, and then we would be able to add. So it's this. This is the first one. This is the other one plus pack. Okay, and then we would be able to finally say pack Diablo address. Okay, now for this to work we actually need RDI RSI. Let's see if we have that. Rob gadget RSI we have, RDI, yeah, unfortunately we don't have them together. So what we have to do is we're going to use pop RDI, and then we have this instruction, and we're going to put something into R15, but yeah, it's going to be something we don't really care about, and then use pop RSI. We don't have anything else to do. So let's use pop RSI R15, pop RSI R15 gadget address. This is it. So then we're going to do it like this. We're going to say pop RDI gadget red gadget address. We're going to pass it the first argument. Then we're going to say pack of pop RSI R15 gadget address plus this one, and then we're going to say Diablo address. It's kind of a mouthful, but it's the no, we're missing something. We also have to say something like pack 0. Why do we need this pack 0?
We need to align the stack.
No, it's because we use pop RSI R15. This is going to go into RSI, but we need something to go into R15. This one. We need two elements on the stack. So when this gets called, it's going to say pop RSI, pop R15, and then the red, pop red. It's going to pop this into RSI. It's going to pop this into R15. It's going to then return to this address. The weird thing, however, is it's not going to work. Why isn't it going to work? It's because, and this is something you can look here, the overflow was 128 bytes. So it's actually, if we overwrite 64, then we have +8. We are overwriting a lot of information. Sorry. that is not going, this information is too big, the payload is too large. It can't get all inside the buffer. This is one of the major issues when doing exploiting. You don't have enough space on the buffer. So this one is going to work. I'm still going to try to do a call of the Diablo part. So let's do it like this. This is going to work because all these items should fit into the payload buffer. So we have 72 plus 8, 80, 88, 96, 104, 112, 120. 120, 128. It may not work. Let's see. It worked. It's on the limit. So this one worked. This one above won't work because the payload is too large. Let's add it here just to say this. It won't work. Payload is too large. I know you're tired, so I know this is going to cause a lot of headaches. This is kind of the basics. I want to go through all these items. I know it's a lot to chew at this point. These are things that are going to be part of this session. I summarized this by stating again that it can't be thoroughly clear from the first time because it's kind of a new way of thinking with the stack and everything, but as you work on it, it becomes more clear, and you're going to enjoy it very much, seeing kind of this clever way of reusing small bits and pieces of code for actual attacks. If you have any sort of final questions, this is the time for them. Otherwise, what I suggest is we're going to split in teams, and I would suggest to have 15 minutes break to clear your mind, because you're going to need that before getting back and starting work on the actual challenges. That will also give me the time to push these snippets on the repo, so you can look at them and test them again yourselves on your own systems. Any final questions, please?
Just a basic curiosity from my side. What is the connection between this stuff and oriented programming?
What is, sorry,
The connection between this and oriented programming.
What do you mean oriented programming?
The session isn't called return oriented programming or something like that?
Oriented, no, it's not oriented programming, it's return oriented programming.
Okay. That makes more sense.
So this is the return oriented programming, because you have return gadgets, and you use return gadgets for code reuse, and you have this ROP. This is ROP, return oriented programming. You also have something that's called jump oriented programming. You have something that's called DOP, data oriented programming, but ROP and JOP are the most so this is why it's called ROP gadget, right? Return oriented programming gadgets. And if you look at them, you can see that most of them end with the ROP, but with the red, but you also have jumps. So this is jump oriented programming. This is return oriented programming. There is no call oriented programming. This is also part of jump oriented programming, because call and jumps are seen as very similar. Yeah, it would have been kind of interesting. Yeah, this is an interesting 90 minutes discussion, but what does it have to do with ROP? So this is ROP. When you talk about ROP, you talk about return, you talk about code reuse, you talk about gadgets, you talk about chaining gadgets together. Alright, that being said, let's end it here. I'm going to end the recording.